All right, so start of the new unit. Our next unit's going to be on functions. Okay, so graphing and using our different function types in order to investigate actual functions. So starting off, we're going to look at our parent functions. If you took Algebra 2 at Champ, you've probably seen this before. We're going to go through this pretty quickly since this should be a refresher, but we're going to start by looking at all of my basic parent functions, and then we'll talk about the transformations. So I'm going to zoom in a little bit here first because we're just going to focus on quadratic and square root at first. So looking at my quadratic function, the reason why we're going to look at quadratics and squares together is because they are inverses of each other, so they're related. Now, my basic ordered pairs for a quadratic function, 0 in the middle, 1, 2, -1, -2. So plugging in those x values, I get +4, +1, 0, 1, and 4. Now to graph these, 0, 0, 1, 1, 2, 4. -1, 1, -2, 4. And then I'm going to draw my parabola. And again, we do call this a parabola, right? My U shape. Now, domain and range. My domain are all of my x's, and my range are all of my y's. Now, when I talk about my domain, I always want to go from left to right. So when I look at my graph here, starting all the way to the left, moving all the way to the right, I see that I'm not missing any of my x values. So my domain would be all real numbers, and we represent that in a number of ways. The easiest being my uppercase R, right? So that stands for all real numbers, so that way we don't have to write that out. Now, using interval notation, those are my parentheses and brackets. Since I'm going from -infinity to +infinity, and I can't equal infinity, they would both have parentheses, right? I only use brackets if I can equal that number. Since I can't equal infinities, -infinity to infinity. Now, the last way we can represent this is with an inequality statement. So -infinity less than x less than infinity. Now, these all say the same thing, okay? So pick whichever interval or whichever notation you like the best and kind of run with it, okay? Now, my range are all my y values, so I want to go from bottom to top. So when I look at my graph here, I see that this thing bottoms out right here when y equals 0. So we can do interval notation, and that's what I'm going to use after this problem. I'm only going to use interval notation, but I'm going from 0 to +infinity. So I have that bracket there because I have the value 0 included in my range. Another way we can say 0 less than or equal to y less than infinity, or just saying y is greater than or equal to 0. Okay, so those are your two options there. Again, I'm going to stick with interval from here on out. All right, now looking at square root function, again, this is the inverse of my quadratic. Okay, and with inverses, we switch our x and y's around. So I'm going to start with 0 in the middle. Okay, square root of 0 is 0. Now my next point on the quadratic table was 1, 1. Flipping those around, it still stays as 1, 1. Now, I'm not going to have 2 as my next x, right? Because the square root of 2 is a decimal, and I don't want to graph decimals. So I want to think about the next perfect square. And if you look at the quadratic, right, if I just switch my x and y's around, right, the next perfect square is 4. And that gives me 2. Now, going the other way, negatives. I can never plug in a negative number under a square root. So we have no negative x values. Okay, so that part of the table we just leave blank. So graphing this, I have 0, 0, 1, 1, 4, 2. All right, domain left to right. So this thing stops at 0 and goes to positive infinity. Same thing with the range. It bottoms out at 0 and goes up to infinity. All right. Now, the next two we're going to look at are right below it. We're going to look at the cubic function and the cube root function. Okay. So again, we're going to look at these together because they are inverses of one another. Okay. And that makes them related in that we flip around our x's and y's to find the other. So looking at the cubic function first, right, x to the third power, I'm going to start with 0, 1, 2, negative 1, negative 2. So plugging in 0, that gives me 0, 1, 1. 2 to the third power is 8. Now, the cool thing with cubic functions is that I'm now allowed to use negative numbers, right? That will give me negative answers. So negative 1 to the third power would be negative 1. Negative 2 to the third power, negative 8. Now, when I go to graph these, I only want to focus on what I call the big three, okay? So those big 3 points are the only ones that I really need to focus on when I'm graphing cubics. So 0, 0, 1, 1, negative 1, negative 1. So it's always going to give me that tiny line segment, okay? Now for cubics, this is my shape. Okay, and I call this the vertical squiggle. Okay. For cubic and cube root, the domain and range are the same in that we have all real numbers for both. Okay. So cube root is the inverse, so that means that I'm going to flip my x and y's, but the big 3 are still the same. 0, 0, cube root of 1 is 1, cube root of negative 1 is negative 1. Now, flipping my y's and x's, the cube root of 8 would give me 2, and the cube root of negative 8 would give me negative 2. But again, I just want to focus on those big 3. All right, so graphing those, again, I get that little line segment, 0, 0, 1, 1, negative 1, negative 1. It's just that this time, my graph is going to look like this. Okay, so I call this my horizontal squiggle. Domain and range are still all reals, all reals. Okay. All right, the last two functions we're going to talk about on this side of the notes. Absolute value and reciprocal function. So absolute value you guys have seen before. 0, 1, 2, negative 1, negative 2. Remember, absolute value, whatever's on the inside, it's always going to spit out a positive number. So 0, 1, 2. Negative 1 would become positive. Negative 2 would become positive. So on my graph, 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. Domain, all real numbers. My range, I'm going from 0 to positive infinity. All right, rational function. So rational, meaning fraction, right? Which is why I have my fraction function here with x in the denominator. So starting with 0, if I plug in 0, that gives me 1 over 0, which I can't have. So when x is 0, I have an undefined function. 1 would be 1 over 1. 2 would give me 1/2. Negative 1 would give me negative 1. Negative 2, negative 1/2. So again, I'm really only going to focus on the 3 in the middle here. Now, that 0 being undefined tells me my asymptotes. Okay? So, when x is 0, y doesn't have an answer. So there are my asymptotes. Now, I have the ordered pair 1, 1 and negative 1, negative 1. negative 2, negative 1/2, 2, 1/2. So my graph looks like this. And these are called my boomerangs. That's what I always call them. Now, domain and range of rational functions. It's easier to say what the function can't equal as opposed to saying what all it does equal. So in this problem, we would say that the domain is everything except x cannot equal 0. Same thing with the range. It can be anything except y can't equal 0. Okay? Now, the last function type we're going to talk about is something called the greatest integer function. Okay, so the greatest integer function, or we also call it the step function. And you'll see why we call it the step function here in a second. But before we can start graphing it, we need to talk about, well, what am I actually doing here? So the step function, the notation here is a little bit wrong. It is a double bracket. Okay, so make sure there's brackets around the brackets, okay? Now, when I want to solve or find a value and plug it into the greatest integer function, what I'm going to be doing is I'm always going to round to the left integer on the number line. Meaning I'm always going to round down. Okay, so for these problems, I'm going to draw out the number line so we can kind of see what's to the left of it. Okay, so 5 is on the integer 5, so that doesn't change. Okay, so if it's an actual integer, it just stays as that integer. So here's 4, here's 5, here's 4.7. So round it to the left integer, round down. So this would equal 4. 0, 1, here's 3/8. So we round down to 0. Now, the trickiest ones are negatives. Here's negative 1/2. So I want to round down or to the left. So this is actually going to round to negative 1. Okay, so be careful of that with negatives. E square root of 2 is in between 1 and 2, so it would round down. Pi is 3.14. So it would round down to 3. Okay. Now, let's think about graphing this thing. Let's start with 0. Okay, if I plug 0 into my integer function, it's just going to be the integer 0, right? So let's plug in some stuff between 0 and 1. 0.1, I would get 0. 0.4, 0. 0.8, still 0, right? Even if I plugged in 0.999, that would still spit out 0. The only time that's going to change is once I jump up to 1. If I plug in 1, I get 1. 1.2, still 1, right? And so on and so on. So what that would look like on a graph, okay? So 0, 0 is my point, and everything between 0 and 1 is going to be 0, right? Except for when I get to the number 1. That's not going to be 0 anymore. So I would have an open dot here, and it jumps up to 1. Everything between 1 and 2 is going to equal 1, except for 2. It's going to jump up to 2. And I just follow that pattern. Same way negative, right? Negative 1 would equal negative 1, and everything in between 0 and negative 1 would be negative 1, except for 0. And just follow that pattern. So domain. do I miss any x values here? And the answer is no, right? All of my x values are taken care of. So this would be all real numbers. Range, are all my y's taken care of? Well, no, right? I have these jumps, these steps, okay? So this is why it's called the step function, right? I jump from 0, and then I jump up to 1, and then I jump up to 2, and then jump up to 3. So it's missing all the stuff in between those numbers. So my range is just the integers, and the way we represent that is with the uppercase Z, okay? And we put the little extra bar in the middle, okay? That means integers, okay? So those are my function families that we're going to be using. Now let's talk about my shifts real quick. So anytime something is inside of the function, so inside the square root, inside the square, right? That is going to mess with my horizontals, okay? My domain. So these are going to mess with my x's, okay? And they're always going to be the opposite of what's presented. If it's outside of the function, either in front of or add it to the end, right? That's going to change things vertically. It's going to be whatever's shown, right? And it's going to mess with my range or my y values, okay? Now, before we start looking at this, I want to first write the basic form of a function, okay? So this represents any function type. So f of x equals a f of c x minus h plus k. All right, so that's the basic function, and you can plug in any of the function types we just talked about in for f, okay? Now, if you look at our notes here, everything's as c, so I want us to change things. So for the first two, instead of plus c and minus c, it's going to be k and k. On the inside here, where it's x plus c, x minus c, we're going to change those to h's. Okay. Those two are good. This one down here, instead of the c in front, we're going to change that to a, and then the rest are good, okay? So, adding k or subtracting k, that's outside of the function. So if I'm adding k, that's going to be shifting up. If I'm subtracting k, down. Okay. Now, these two are inside the function, so h is always the opposite. Okay? So if it's x plus h, that really means h is a negative number, and I'm going to shift left. X minus h means h is positive, so I'm going to shift right. Okay, that negative out front, that's going to flip over the x-axis. So when I see a negative out front, I want to think about flipping up and down. Okay. Negative on the inside, all right, so that's the new transformation. We haven't dealt with anything on the inside attached to x before. And we're not really going to focus on that too much today. We'll do a lot of that tomorrow, okay? Negative on the inside, though, that's going to flip over the y-axis. So when I have a negative on the inside, I want to think flip left and right. Okay. Now, my compressions and stretches here. When A is on the outside, this is going to be my vertical stretch or compression. Okay, so it's going to pull it and make it skinnier, or it's going to scrunch it, compress it, and make it fatter or wider, right? When I have an A out front, I want to multiply all of my y values by A. Okay. Now, when I have C on the inside with the X, that is going to be my horizontal stretch or compression. Now, since it's on the inside, right, it's going to be the opposite. So you can either think divide by c or multiply all the x values by 1 over c. And that's it.